Welcome back to Industrial Problem Solving. My name is Dave Roysum. We're almost done with the problem-solving process that began with defining the problem, then proceeded to the core, which is figuring out what makes the problem work, which then leads to option generation. In the last module, we discussed decision-making. However, merely deciding does not get the job done. Someone has to do something effective, perhaps something different than done in the past. The fundamentals of the work breakdown structure were codified by the U.S. Navy in the late 1950s. It has been refined and used by millions of project planners ever since. A project is first broken up into smaller tasks. Each task is described in detail. The required people and money resources are listed. Finally, any prerequisites are also listed. Prerequisites are critical to, excuse the pun, the critical path method. This structure lends itself to computer programs because the elements of the subtask can be listed in a database, or spreadsheet if you like. In this example, we detail the elements for a routine kitchen cleaning. Note the dependency we listed earlier that you need to clean the counters before you clean the floor. The critical path method is one way, perhaps the best known way, to display project flow. Here we show cleaning several rooms in the house. In this example, we illustrate the advantages of parallelization to shorten the total duration of the project. Here, for example, we are cleaning the living room rugs while waiting for the kitchen floor to dry. The critical path, while useful, has several limitations. The primary ones are that schedules, and especially resources, are not easy to see. In contrast, the Gantt chart is great at displaying schedules and resources, but not so good at showing dependencies. No problem. Modern software can switch between the work breakdown structure inputs, the CPM and Gantt chart outputs, as well as other useful tools such as keeping track of cash flow or people's schedules. Two measures of project success are being on time and within budget. However, let me mention a more important criteria before we proceed. That is, people will soon forget if the project is a bit late, but they will never forgive you if the machine performs poorly for its life. So, what happens if you are late? You can restudy the problem to see if there are bottlenecks that can be avoided that were not anticipated in the first project plan. You can consider parallelizing efforts. An example is to install a machine using 2 12-hour shifts or 3 8-hour shifts instead of working a normal business day. Note that parallelizing and other attempts to speed up a project are very likely to cost more money. On the other hand, you might be over budget. While you can sometimes throw money at a project to speed it up, you usually can't throw time at a project and save money. In any case, notify your customers, contractors, and all involved if you are going to be late. In any case, notify your customers, contractors, and all involved if you are going to be over budget. In any case, learn from your mistakes. I love industrial engineering. Almost took it up as a profession, in fact. It is so super practical. One thing the IEs study is failure rate. It is a science known in statistics as the Weibull curve, or more commonly known as the bathtub curve. Not only does this curve apply to parts, it can apply to projects and sometimes people as well. On a machine, the first weeks or months after a startup might well be pretty rough. This part is known as infant mortality and is plagued with parts that don't fit or break early. The next part of the curve is from 1 year to perhaps a decade or two, where the machine will, hopefully, hum along as good as it's going to get. Finally, the machine, as well as you and I, are going to get old, creaky, and slow down as the parts wear out. We are all so super busy that we barely finish one project before we are on to another. Being so super busy is not conducive to learning. Just because the project seemed like a success does not mean we did the right thing. Success could be mostly due to someone else, or perhaps mostly due to luck, such as getting an easy assignment. We should also learn from mistakes. At the first company I worked for, the Beloit Corporation, we regularly told and retold war stories. War stories are a narrative of some part or project that was a disaster. These stories serve two purposes. The first was to teach everyone what to avoid. The second was to warn you that your turn for failure will come too, as well as both you and your company will probably survive. My biggest mistake to date is costing one of my best clients about $250,000 of a rebuild that didn't help the problem. Both myself and that company are still doing fine, thank you, and we both learned from the process. Yet, neither of us is gun-shy. We attack problems with the same studied boldness as before. The problem with many company cultures is that war stories are not considered politically correct. They are deemed too negative. And you want to be a positive person to be the most promotable. Well, okay, fine. But this taken to extreme is one of the pitfalls of problem solving that we will cover in the next module. Those that don't learn from history are doomed to repeat it, as the saying goes. One area that Beloit truly excelled in, that most other companies do poorly, is reports. In most cases, the technical people were required to write a report any time they left the office. In the case of customer visits, that would be keyworded by customer, location, machine, order, if applicable, contacts, and summary paragraphs. These were database, so anyone and everyone could look at the history of any customer, machine, type of problem, and so on. So, what does it take to be a good critical thinker or a good industrial problem solver? Well, it starts with knowing the area, which would, of course, include reading and literally going to school. There are dozens of great short courses in any number of must-know topics. I teach 2-day courses in web handling, converting, winding, and problem solving. AIMCAL also has courses in coding, drying, extrusion, slitting, drives for web machinery, and more. But critical thinking is way more than book learning. It is an attitude and a mindset where one cares about getting the correct answers quickly and efficiently, but does not care about how pleasant those answers are. It is the flexibility to believe that something is true and may not be true at the same time, until there is a preponderance of evidence in one direction, at which time one must commit to a conclusion. Even then, though, we would be totally willing to drop our most cherished beliefs if new evidence came in that indicated the need. So, let us close with a prayer attributed to Dr. Reinhold Niebuhr, even though it's probably written much earlier by someone else. God, give us the grace to accept with serenity the things that cannot be changed, the courage to change those things which should be changed, and the wisdom to distinguish the one from the other. Thank you so very much for joining me in this problem-solving process. I hope I've made the case that planning is a necessary but not sufficient part of success. It is not sufficient if the problem definition was incorrect or overconstrained. It is not sufficient if, for example, the core of problem solving is weak and you really don't understand the problems because you were rushed. I hope I've made the case that learning from both your successes and from your mistakes is good. But please pass that on to others so they don't have to make the same mistakes. Yet, we're not done. In fact, I've saved the best for last. In the next modules, we will list the many pitfalls to the problem-solving process. It is a ton of fun. Stay tuned.